turns out there are actually only certain symmetry elements we can have in combination with each other. Because if we put in a mirror plane and then we try and put in another mirror plane that's, for example, perpendicular to it, that will then restrict certain symmetry that we have within the system. And this is what defines our space groups. And it turns out that a combination of these crystal our unit cells and these symmetry elements, we've only got 230 ways that we could possibly do this and still have something that's translationally periodic in 3 dimensions. And this defines our space groups, and you might have seen these before. So, for example, here I'm showing a picture of what's called the P21 upon C space group. And we might be able to start to see things that we recognize in this. So P means that it's primitive, 2-1 is a 2-1 screw axis, and C is a C glide plane. And I've got a picture here where we've got certain symmetry. This is my overall unit cell, and we've got certain symmetry elements within it. We've got centers of inversion. We've got screw axes shown here. You can see here that this angle is non-90 degrees. It's got a beta angle that's non-90 degrees, and that therefore means that this system is actually monoclinic. And if I go back and look at my minimum symmetry requirement for a monoclinic is 1 dyad or mirror plane. And in fact, this has a dyad. In fact, it's a screw axis, but that is going to be my minimum symmetry requirement here. And as we say, certain combinations of symmetry elements can go together, and these can become quite complicated. And so these are my space groups that I'm seeing here. So this is a picture of a much more complicated space group. This is the I4 upon MMM space group. This is a tetragonal space group that I'm showing here. And we can see lots of different symmetry elements on here. And so people draw up tables, and there are various tables online showing these space groups that you can look up. But it's worth being aware of these space groups and what they mean and understanding the crystal symmetry of one of these things. Now, what does this mean for our diffraction and things like that, or what we're trying to study? Well, if a material is a crystal, then it will have one of these translationally periodic structures in 3 dimensions. As a slight disclaimer here, the definition of a crystal has changed slightly recently by the International Union of Crystallography to account for quasi-crystals. But in a simplistic way, what we can say is that it's something that shows this periodicity. Now, most crystals that most people will study will show this 3D translational periodicity. If you're going into quasi-crystals, it shows periodicity, but it will be in a higher dimension. But for most of the things that most people will study from day to day with diffraction, we're looking at crystals and something that has that 3-dimensional periodicity to it. And that means that we can describe it with a lattice. It means that we can describe it with a 3D unit cell. And that 3D unit cell will have some sort of space group associated with it that defines the symmetry elements that we observe within it. So it might be something like one of these, like P21 upon C, or something like that. So when people are talking about a particular crystal structure, what they're referring to very often is that something with that translational periodicity, where we're defining it by a unit cell, and that unit cell we can define with one of these space groups that we can look up and tabulate online. And there are various resources that I'll make available, or I'll give links to in some of the notes, links to where you can look up these space groups and look and work out what these crystal structures are and consider these crystal structures for a particular material.